Studies Section 4, Two-Variable Regression Analysis. Introduction. In this study section, you will explore the theory underlying the simplest possible regression analysis known as the two-variable case. You will also examine the significance of stochastic disturbance and sample regression. Learning outcomes. When you have studied this section, you should be able to show the difference between linearity in variables and parameters, discuss the significance of stochastic disturbance term, differentiate between population and sample regression, linearity in variables. In its simplest form, the meaning of linearity is that the conditional expectation of y is a linear function of x, such that into bracket y over xi is equal to beta 1 plus beta 2 xi. Question 10. Geometrically, the regression curve in this case is a straight line. In this interpretation, a regression function such as e into bracket y over xi is equal to beta 1 plus beta 2 xi squared is not a linear function because the variable x appears with a power or index of 2. Linearity in parameters. Another measuring of linearity is that the conditional expectation of e into bracket y over xi is a linear function of the parameters. Betas and may or may not be linear in the variable x. That is, a function is said to be linear in the parameter, say beta 1, if beta 1 appears with a power of 1 only and it's not multiplied or divided by any other parameter, for example, beta 1, beta 2, beta 1, beta 2, and so on. In this interpretation, e into bracket y over xi is equal to beta 1 plus beta 2 xi squared is a linear regression model, but e into bracket y over xi is equal to beta I is equal to beta 1 plus square root of beta 2 xi is not. The latter is an example of a non-linear in the parameters regression model. Of the two interpretations of linearity, linearity in the parameters is relevant for the development of the regression theory. Linear stochastic regression assumption. Let's express the deviation of yi around its expected value as follows. Mu I is equal to yi minus e into bracket y over xi, or yi is equal to e into bracket y over xi plus mu I. Question 11, where the deviation mu I is an unobservable random variable, positive or negative values. Technically, mu I is known as the stochastic disturbance or stochastic error term. Equation 11 means that yi given xi, for example, expenditure y given its income level can be expressed as the sum of two components. One, e into bracket y over xi is simply the mean y expenditure of all the observations. This component is known as the systematic or deterministic component, and 2, mu I is the random or non-systematic component. If e into bracket y over xi is assumed to be linear in xi, then it could be written as yi is equal to e into bracket y over xi plus mu I is equal to beta 1 plus beta 2 xi plus mu I. Equation 12. Taking the expected value of equation 11 on both sides, we obtain e into bracket yi over xi is equal to e parenthesis open e bracket open y over xi bracket closed parenthesis closed plus e into bracket mu I over xi is equal to e into bracket y over xi plus e into bracket mu I over xi, question 13. We assume that the expected value of a constant is the constant itself, given that e into bracket yi over xi is the same as e into bracket y over xi. Thus, equation 13 implies that e into bracket ui over xi is equal to 0, equation 14. At this point, it could be said that equation 10 and 12 are equivalent forms of e into bracket ui over xi is equal to 0. However, the stochastic specification in equation 12 has the advantage because it clearly shows that there are other variables beside x, say income, that affect y expenditure, and that an individual y cannot be fully explained only by the variables included in the regression model. Significance of the stochastic disturbance term. The stochastic disturbance term, mu I, often represent all those variables that are left out in the model but that collectively affect y. The following are the reasons for including stochastic terms in economic models. 1. Stochastic term is used in order to keep the regression model as simple as possible, given that the theory is not explicit enough about other variables that will be included. This is called parsimony principle. 2. Even if the theory is explicit about the variables to be included in the model, the issue of the functional relationship between the regressand and regressors is another case to be considered. For example, is consumption expenditures a linear invariable function of income or a nonlinear invariable function? In the case of the former, it will be equal to beta 1 plus beta 2 xi plus mu I is the appropriate functional relationship, while if it is later, yi is equal to beta 1 plus beta 2 xi plus beta 3 xi squared plus mu I will be the correct specification. 3. Sometimes we may know the excluded variables and therefore consider a multiple regression rather than a simple regression. However, we may not have quantitative information on these variables. That is, the data that will be in take 2. That is, the data that will be ideal for these variables might not be available. 4. There might be vagueness of theory such that determining the behavior of a variable might be inexplicit. It is possible to know that weekly income X influences weekly consumption Y, but we might not know other variables affecting Y. In this case, mu I could be used as a substitute for all the excluded variables in the model. 5. Even if we succeed in introducing all the relevant variables into the model, there is bound to be some intrinsic randomness in Y that cannot be explained no matter how hard we try. The disturbances, the mu I, may well reflect this intrinsic randomness. 6. Another factor that could necessitate the use of stochastic term in the model is the problem error in measuring variables. Although the classical regression model assumes an accurate measurement between variable y and x, in reality, the data may be liable to measurement error. For instance, in theory, permanent income determines permanent consumption, but in reality, these data are not directly observable. What researchers do is to use proxy variables such as current consumption Y and current income X that can be observable. Since these observed variables might be the same with the actual variables, there is the problem of measurement error. The disturbance term U will be appropriate to represent the measurement error. Population and sample regression function. In earlier discussion, the variables are used in terms of their population values, which is the actual value of these variables. However, in reality, what is often estimated, that is the sample values of y corresponding to some fixed x's. Therefore, the population regression function is estimated on the basis of sample information. The sample regression function represents the sample regression line and can be written as yi estimate is equal to beta 1 estimate plus beta 2 estimate xi, equation 15, where y is y cap, which is the estimator of e into bracket y over xi. Beta 1 cap is the estimator of beta 1, while beta 2 cap is the estimator of beta 2. An estimator, which is also known as sample statistic, is the rule of formula or method that shows how to estimate the population parameter from the information provided by the sample at hand. The numerical value that will be obtained by the estimator in an application is known as an estimate. Just as the population regression function was specified earlier, so also the sample regression function can be specified in its stochastic form as yi is equal to beta 1 plus beta 2 xi plus mu I, equation 16, where the mu I represents the sample stochastic or residual term. Conceptually, mu I is analog to ui and can be regarded as an estimate of mu I. The primary objective in regression analysis is to estimate the population regression function. yi is equal to beta 1 plus beta 2 xi plus mu I, equation 17. On the basis of the sample regression function, yi estimator is equal to beta 1 estimator plus beta 2 estimator xi plus mu I estimator. The difference between the actual value population and the estimated value sample is called the residual. Studies section summary. In this studies section, you were exposed to the concept of linearity in variables, parameters, and stochastic regression. We capped the section with distinctions between population and sample regressional functions. This is the end of studies section 4. Thanks for listening.